Field emission is the one wherein which field is given? The electric field over here. Einstein's mass energy equivalence E is equal to mc square, as well as we know that energy of a photon is equal to h nu. With respect to these two concepts, we will have to derive an equation. And the filament was heated with a low voltage power supply. There was a low voltage power supply was given to a filament in order to heat it up. Hello everyone, I'm Brinda, Faculty of Physics, welcoming you all to Chapter 11. Chapter name is Dual Nature of Matter. In today's concept, we have to check the dual nature of matter as well as radiation. Double the nature. Double nature means the light behaves as particles as well as waves is what was studied over here. What is meant by the electron emission? Electron emission means electron is getting emitted out. That means to say that there is a liberation of electrons from the surface of the metal. It's a simple electron emission where it happens from the surface of the metals. But in order to study these, there are many types of electron emission. One is your thermionic emission. Secondly, it is your field emission and photoelectric emission, and finally it is secondary emission. So we'll have to know what is thermionic emission, what is field emission, what is photoelectric emission and secondary emission. For which thermionic emission, first word itself tells it is with respect to temperature. Certain amount of high temperature is given to a surface of the metals such that the electrons from the temperature meets certain binding energy and it just removes the electrons from the surface of the metal. Such kind of an emission is called as thermionic emission. The second sort of emission is called as a field emission. Field emission is the one wherein which field is given? The electric field over here. So the electric field, certain amount of electric field is being induced into the surface of a metal so that there is a electron which gets emitted out due to a strong electric field. Similarly, photoelectric emission in the sense certain amount of radiations is involved or allowed to fall on the surface of the metal such that the electrons are just ejected out of the metal surface due to the radiations. And secondary electron emission is nothing but it is the primary electron, certain high energy electron is allowed to fall on the surface of the metal so that the certain electrons is allowed to move out of the surface of the metals. This is how exactly it is divided as thermionic emission, field emission, photoelectric emission as well as secondary emission. That's all about your electron emission concept. Next we have Einstein's photoelectric equation. Einstein's photoelectric equation turns out to be there is a certain amount of energy which is provided to a surface of metal which is useful in liberation of the electron. The same concept has been carried out with the help of an experimental setup in an evacuated tube. There is a window opening here through which you have anode as well as the cathode which is connected to a certain set as well as a commutator. So whenever there is a fall of incident radiations, the electron is emitted out and is collected with the help of another plate, and then there is a production of electric current. That means the proportionality concepts have been studied, that is photoelectric observation, photoelectric effects observation have been seen, which means to tell that due to this, that is the photoelectric current is directly proportional to the intensity, which means to say it depends on intensity, and your saturation current depends on intensity, but your potential energy is independent of intensity. This is what the observation is made by the photoelectric effect observation, Einstein's photoelectric observations. So now with the help of these set of things, there is an equation which is given, and that equation holds good with respect to a photon is released. So photon is, the energy of a photon is H nu, and there is a certain set of work function for a work to be done in order to remove the electrons from the metals, that is phi naught, as well as the work done is nothing but the kinetic energy. So here we have use K max, which is equal to half mv square. V is velocity, maximum velocity. So the set of Einstein's equation is given as energy is h nu is equal to the work has to be done with the kinetic energy. So you can, Einstein's photoelectric equation can be turned out as h nu minus phi naught is equal to half mv square, and this is max. This is known as the Einstein's photoelectric equation, one of the most important component with the help of this setup. So for this separate setup, experimental setup, there is a explanation on with respect to the procedure. The procedure is simple, which was told earlier. From a window there is a fall of radiations which will fall on the plate, and there is an emission of the electrons which will result in the current which is produced. And what are the observation you can see here with respect to the intensities, whatever is given over here. So that's all about your Einstein's photoelectric equation. With the help of this, we have concept called as de Broglie wavelength. So for which we have Einstein's mass energy equivalence E is equal to mc square, as well as we know that energy of a photon is equal to h nu. With respect to these two concepts, we will have to derive an equation. Since we know this, equating these equation 1 as well as equation 2, you have mc square is equal to h nu. Keeping m on one side, and you have h nu divided by c square. So we know that momentum is equal to mv, so you can just retain it as mcv is a velocity. So here we are considering the light, so it is velocity of light. So on equating this equation with in place of m, you have to substitute equation 3. So we have p is equal to h nu divided by c square into c, cancels. Since we know that nu is equal to c by lambda, we can equate p is equal to h, nu is c divided by lambda, and c over here, c cancels. So we have p is equal to h by lambda, or lambda is equal to h by p. This is for a light. If you are considering a material, then p becomes equal to mv. Therefore, we have lambda is equal to h divided by mv concept. And we know that kinetic energy is given as half mv square. So mv square is equal to 2 times the kinetic energy. So in the terms of, we know that P is equal to m into V. V is equal to P by m. Substitute this equation towards here. So m into P square by m square is equal to 2 times the kinetic energy. 1 m cancels. So P square is equal to 2 mk. P is equal to root of 2 mk. P is nothing but mv is equal to root of 2 mk. So you can substitute this equation for this, that is lambda is equal to h divided by root of 2 mk if a material is considered. So if you have to convert the energy, kinetic energy, into electron volt, then we can write that as lambda is equal to h divided by root of 2 times m into the electron volt. So this is how exactly the de Broglie wavelength has been given in order to give the nature, the particle, that is dual nature, particle nature and wave nature. This is a concept from the chapter of dual nature of matter. So that is all about your de Broglie wavelength concept. Next is, there was an experiment in order to prove certain set of component of a light as what sort of a nature it is. So that Davison and Germer experiment, it has been named. So what exactly it is? There is a setup which was undertaken to confirm a wave nature of a matter, and the filament was heated with a low voltage power supply. There was a low voltage power supply was given to a filament in order to heat it up. The electrons which were emitted by a filament are accelerated with the desired voltage with the help of a suitable high power supply. So there was a filament through which the high power supply was being connected. So the electrons were emitted from the filament, and the filament was collimated with the help of a cylindrical component, and there was a nickel crystal here. So the anode A is in the form of the cylinder. So where a fine hole through which the beam is collimated, the beam will be collimated and it is made to fall on the nickel crystal. The intensity of the electrons are scattered. It is detected by a detector which is connected to a galvanometer. Galvanometer shows certain deflection, and this deflection is directly proportional to the intensity of the incident electrons. So deflection will be directly proportional to intensity. That is nothing but which proves the Einstein's photoelectric conditions, that is the electrons imagine the electrons, number of electrons moving, that is a photoelectric current. How many number of electrons are moving, so much of photoelectric current is being produced, which is directly proportional to the intensity. So that is what actually is proved with the help of the Davison-Germer experiment. And this experiment confirms the wave nature of the light. So in today's class, we have dealt with the chapter wave optics, in which we have studied the Einstein's photoelectric equation with respect to its experimental procedure as well as its observation, and types of thermionic or types of emissions we have studied with respect to thermionic field emission, secondary emission as well as the photoelectric emission. With the help of all those things, we have confirmed the wave nature of the particles with the help of a Davison-Germer experiment. So let us all meet in our next upcoming session. Until then, have a good day. Thank you.